the next speaker, we said that before, and his talk is entitled Automating Cryptanalysis, Automated Reasoning and Structural Links Between Attacks.
Thanks for introduction, by the way. I am trying to find a way to share my presentation. It's still... Okay. Thanks, Soma, for introduction. Hi, everyone. I am Hussein from Ruhr University, Bochum. Sorry, this is slide number 97. For those who are hungry. Okay. Yeah, I'm Hussein. Nice to meet you all. From Ruhr University, Bochum. I have the great honor of being the last thing standing between you and lunch. It's a tough job, you know, because you're at the peak of your concentration now. But I will try my best to make it worth the wait for lunch. If not, then lunch will taste even better. Don't worry. So I don't know why I chose this very complicated topic for this talk, but what I want to talk about is really simple. I just want to talk about the relations between symmetric key attacks and how we can exploit these relations when it comes to automated discovery, right? But what I want to present is a mix of my collaborations with these nice guys. I want to thank all of them for collaborating. Yeah, let's first take a look at the anatomy of symmetric key attacks. We talked about a bunch of the attacks since today morning. For example, differential attack, linear attack, boomerang, zero correlation, and so on and so forth. But what's common between them? Almost all of these attacks follow almost the same anatomy, as you can see in this shape. They have two phases, the distinguisher phase and the key recovery phase. What was that? Okay. For the distinguisher phase, we typically find a property for part of the cipher which behaves differently from that of an ideal cipher. Let's say a differential trail. For an ideal cipher, the number of pairs that satisfy a differential follows kind of normal distribution with a certain mean and variance. The mean is almost to the power of minus n when n is the block size. But for the real cipher, the number of pairs that satisfy the differential typically, again, follows the normal distribution, but it typically has a larger mean, which deviates from the mean of the ideal cipher, as you can see in this shape. So this way, we can distinguish between the ideal and real cipher. And typically, we extend this distinguisher to the key recovery part. As you can see, one of the very common methods in key recovery is that we extend the distinguisher from two sides, from top and bottom. And then we guess part of the involved keys and try to do partial encryption decryption to reach to the input and output of distinguisher to check if that property holds or not. This is the way we do the key recovery mostly. And as you can see, there are many things in common between the key recovery techniques. For example, in differential-based key recovery, like in differential key recovery, boomerang, differential linear, we typically use the early abort technique, which is a technique to reduce the time complexity of the attack. Another common technique which was known since, I would say, 2004 is probabilistic extension. Instead of extending the distinguisher with probability 1, we can extend it with probability less than 1, and it has been used in almost all of the attacks on 7 runs of AES. In the context of linear key recovery, we again have some common techniques. The most famous one is a partial sum technique, which is, I would say, the alternative of early abort technique in differential analysis in the context of linear analysis. And we also have the FFT techniques. You see in each category we have a couple of common techniques, but each category also enjoys some techniques that the other cannot. And there are some very generic methods that are applicable to almost any key recovery techniques, like guess and determine attack, or technique and key bridging. The key bridging actually exploits the relation between the keys that are involved in the attacks. we want to save like some guesses. We want to exploit the relation between keys. I don't want to go through the details. I just wanted to give you a big picture of the anatomy of symmetric key attacks. But why do we need to take care of the links between the attacks, the relation between attacks? The answer is easy. We want to save time and avoid reinventing the wheel. If there is kind of a theoretical link or structural similarities between two attack types, so it's best to use that to save time and like avoid inventing new techniques for each attack type. But one might argue that, okay, it's against creativity because when you start something from scratch, it may lead you to something novel. But I would argue the opposite. I believe if someone is creative, they are creative, regardless of having the knowledge or not, right? But having the knowledge, having this big picture in mind and knowing the relation between attacks enables you actually to see the gaps and hidden points out there better that others cannot see. So overall, this should be convincing. If it's not convincing for you, you can take a quick nap for the rest of this talk before lunch. I think you don't have to listen to the rest of this talk. So this is the reason that I want to look at the relation between the attacks. I want to exploit these relations to like reuse the advancements and insights in one attack type in another. Let's say we have two attack types, and researchers have developed different methods for these two, but independently. If there is kind of relation between them, we can take the most efficient tools and methods from one and apply it to another, instead of like developing independent techniques for each one, right? So this is the main motivation of studying the relation between the attacks. Okay, it doesn't work. No problem. Okay. So I want to first look at some theoretical links between the attack in the first part of my talk and show you how these theoretical links can help us to efficiently find attacks. I want to start with integral attack, which is typically the most efficient attack in terms of distinguisher. I would say the most powerful attack in terms of distinguisher is integral attack so far. But when it comes to key recovery, it's not always the most powerful one. I will tell you why. But integral attack is a chosen plaintext attack in which we find a set of plaintext whose corresponding output sum to 0. They have a zero-sum property, the outputs, right? And zero correlation, the idea of zero correlation is finding a linear approximation for the cipher which has a correlation of 0. And these two look completely independent, right? At first glance. There is no relation between them. But interestingly, in Crypto 2015, I think even before that, 2014, another group of researchers unrevealed a link between zero correlation and integral attack. And it says, essentially, any zero correlation can be converted to an integral distinguisher. You don't have to read this theorem. It essentially says any zero correlation distinguisher can be converted to an integral distinguisher. But I will tell you how with a simple example. This shape represents a 6-round zero correlation distinguisher for a skinny. The notations in my slides, the orange represents a fixed linear mask. Red represents any non-zero, right? And the blue represents essentially unknown or like a completely free variable. Okay, we have 3 activeness patterns: fixed, any non-zero, and completely free or unknown. This shape represents a zero correlation distinguisher for 6 rounds of a skinny. According to the theorem, if you want to convert it to an integral distinguisher, you just need to invert the activeness pattern at the input. It means you need to activate those blue cells, and then you will get a balanced property for the XOR of the active cells in the output. Look at this short animation. This is the zero correlation distinguisher. Just invert the input activation pattern, then you will get an integral distinguisher. Okay? It's kind of simplification, but let's get back to the theorem. If you look at this theorem, if you find a zero correlation distinguisher with a kind of higher dimension for the input space, as you can see, the dimension of the input space for the corresponding integral distinguisher is lower. It means, intuitionally, if you have more active cells at the input of zero correlation distinguisher, you will get an integral distinguisher with a lower data complexity. So unlike all of the traditional approach in zero correlation or impossibility differential, where we looked for impossible distinguishers or zero correlation distinguisher with only one active cells at the input and output, here, as you can see, we have a lot of active cells. We would love to have a lot of active cells at the input, because if you convert it to integral distinguisher, the data complexity of the integral distinguisher is lower. You see? So it's kind of converse. But what do we do with this link? Let's see how we discover the zero correlation distinguisher and integral distinguishers. Most of the existing tools for finding zero correlation distinguishers and integral distinguishers are kind of, I mean the tools based on external solvers. I don't mean the dedicated tools. Most of the tools based on general purpose solvers or external solvers are based on negative model. Let me simplify it for you. What it means. Let's say you want to find a zero correlation distinguisher. You essentially model the propagation of linear trails. You fix the input and output, as you can see in this shape. Then you call the solver. If the solver returns a negative answer, saying that the model is unsatisfiable, you have a distinguisher, okay? By negative, I mean this. Most of the existing tools were based on negative model. So what's the basic limitation? The basic limitation is that you cannot extend this model for a unified model for a key recovery. This is the basic limitation, because you have to fix the input-output of distinguisher, and you need to iterate over all of the combination of input and output, which is very large, okay? This is the basic limitation. But there was actually a basic method to find or kind of confirming a given zero correlation distinguisher, and it's essentially missing the middle technique, which was proposed with the seminal paper of impossible differential attack. According to this technique, you just propagate two activance patterns forward and backward such that they contradict each other in the middle. As you can see, for example, there is a contradiction in the middle. One cell should take a 0 linear mask from the top trail, and at the same time, it should take non-zero. So it's kind of contradiction. It's like a proof by contradiction in logic. You give me an input-output activance pattern. I assume that, okay, there is a trail. Then I propagate with probability 1. I achieve a contradiction. Then it's kind of a proof that, okay, this input never propagates to this output. Okay? But this method is just a way to confirm a given input and output pattern, right? It doesn't tell you how to find it. Essentially, it doesn't tell you how to find an input with a lot of active cells, because having a lot of active cells in the input, as I mentioned, is very good if you want to convert it into integral distinguisher, right? Okay. So in Eurocrypt 2023, we proposed a simple method based on external solvers to find actually, we proposed a positive model to find distinguishers. And it works like this. Let's say we want to find a distinguisher for block cipher E. We divide it into two parts, let's say left or right, or up and down, upper and lower. Then we model the propagation of the property, whatever it is, I don't know, linear, differential, whatever it is. We model the propagation of property in forward direction with probability 1. And we also do the same for the backward direction. And we model this propagation with independent CP models or MILP models. And there is no link between them so far, but we put some constraints for the junction between these two that guarantee the contradiction between the two propagation. As you can see, there is no constraint or limit on the input delta U and the output delta L. So if you put all of these constraints, that model the propagation, also the contradiction, together and solve it, any solution of this model is essentially a zero correlation distinguisher or an impossible differential distinguisher, right? The advantage is that there is no limit on the input and output, so it can be extended for the key recovery. But this is only one advantage. Another advantage that I really love more is that you can set an objective function here. The model is positive, right? Any solution of the model is a distinguisher. But now you can set an objective function saying that, okay, please find a solution that maximizes the number of active cells in the input. Then you get an integral distinguisher with minimum data complexity. Let me give you some examples. I should mention that in the follow-up works, we improved this model. In FSE, I would say, I think 2024, we just removed the limit of having contradiction in only one round. We extended it, but it's not very important for this talk. I don't want to focus on it now. Let's look at this example. We found it with our tool. This is a zero correlation distinguisher for 7 rounds of SKCAM. When we were searching for this, we set the objective function to maximize the number of active cells in the input. As you can see in the input, there is only one white cell, which becomes active in the integral distinguisher. It means the complexity of integral distinguisher here is 2 to the power of c. If the cell size is 4, the complexity of this integral distinguisher is 2 to the power of 4, which you can practically verify on your laptop. It's very easy to verify, right? But when I refer to the literature, I found that some researchers actually don't care about these links. For example, in task 2019, there was a nice paper which exploited the algebraic techniques. And but they didn't care about this link between zero correlation and integral, and they found a 7-round integral distinguisher with complexity of 2 to the power of 2c, which is much, more complex than ours, right? The complexity is much worse, it's higher. But there was another example. For 8 rounds, with our simple strategy, we found an integral distinguisher with complexity of 2 to the power of 12 for SKCAM, let's say 64. But that paper, there was another paper by Patrick, co-authored by Patrick Derbes. They used division property for 8 rounds, and they still couldn't find a better, actually, distinguisher. We all know that division property is kind of accurate, much more powerful than our method. You know what is, what is the barrier? Because if you want to find an integral distinguisher with minimum data complexity with division property, the modeling out there is negative. You need to iterate over all combination of the input, right? This is the bottleneck, because you have to check a lot of input patterns. You're stuck in running time. You cannot check all of them. So you just stop somewhere that you have a better result and you report. But to find this with our method, it's just like take less than a second. You just press the enter and you get the result, because it's a very simple model. I hope the advantage is clear. You know, for a strongly aligned ciphers, we should be careful. Sometimes, we are putting too much effort on some accurate model, but we can get the same result with a very lossy model like this. But for a strongly aligned designs, I don't argue this for all designs. This is another example for 10 rounds. As you can see, the paper with algebraic technique could reach to an integral distinguisher with complexity of 2 to the power of 15 times c, but we achieved 12 times c, with again much simpler approach, just less than a second. But the paper by Patrick reached to a distinguisher with the complexity of 47, which is only 1 bit better than ours. Yeah, but again, I would say, in my model, I typically limit the input pattern to take only like any or 0. I don't let it to take non-zero, any non-zero. I believe if I relax the input limit, I can even find something maybe better. But I didn't try that. Maybe just a conjecture. I'm not sure. But so far, I just talked about integral distinguisher or zero correlation distinguisher, regardless of the tweak schedule. We don't exploit the tweak for tweakable block cipher. In tweakable block ciphers, the attacker has a full control over tweak. But how we can find integral distinguishers for two equal block ciphers? Again, we can use those negative models for division property or zero correlation, but the model for division property becomes very hard to solve if you use it for two equal block cipher, because of a lot of copy operation in the tweak schedule, especially if the number of parallel tweak lines is high, like in SKCAM. People who have tried it know very well that it becomes very hard to solve if you model it for a large number of rounds. But interestingly, there was again another link between zero correlation distinguisher of two equal block cipher and integral distinguisher in task 2019. There is a theorem which proposes a miss-in-the-middle-like approach to find zero correlation distinguishers for two equal block ciphers. This theorem says that this is a big picture of a two equal block cipher following the two-key framework. You can see the two-key path at the top, and you can see the data path at the bottom. So in this example, there are Z parallel two-key paths in the two-key schedule. The theorem says that let's Z is the number of parallel paths in the two-key schedule. If you find an input-output mask which activates a two-key cell at most Z times, then this input-output mask gives a zero correlation distinguisher. If you find an input-output mask for this cipher, and an input mask over P and an output mask over C is such that it activates a two-key cell in at most Z times or Z positions, then it gives you a zero correlation distinguisher. And it's a treasure. I would say this theorem is a treasure because let me give you an example. This is 8 rounds of a skinny, but this time I want to propose a kind of related tweak integral distinguisher or chosen tweak integral distinguisher. This is just 8 rounds of a skinny TK2 with 2 tweaky paths. I want to show you how that theorem works. Choose this forward propagation. Just activate everything at the input. And then choose this output acting pattern and propagate it backward with probability 1. Now let's put them together. When you put them together, you will see that if you track tweaky cell number F, it is activated in at most 2 times. I don't know, my pointer doesn't work. But as you can see, the position number F is activated in at most 2 times. According to the theorem, this is already a zero correlation distinguisher. And with all of those active cells at the input, it gives a very, very low data, a low data complexity integral distinguisher, which has a complexity of to the power of 2c because of having 2 active cells in the tweak, not in the data path. These 2 active cells are 2 active cells in the tweak, not in the data path, which are not visible in this shape. Again, we have a tool now, thanks to the relation between zero correlation and integral. We have a very fast tool to find integral distinguishers for two equal block ciphers. And all of these results, as you can see, have been produced in less than a second. If you want to find them with division property, it's a pain, I would say. Don't try that. For Karma version 2, for example, we went up to 12 rounds. I would claim with division property, in practice, it's really almost infeasible to capture this integral distinguisher for up to 12 rounds of Karma V2. This very light and fast model can capture these distinguishers. For example, the designers of Karma V2 apply division property up to 5 rounds. So I wanted to draw your attention to this link. Did you notice the link between zero correlation and integral distinguisher? We used it in terms of discovery, automated discovery of attacks. This is the message of my talk, actually, for PhD students who are studying this field. Please just take a look at the links between attacks before diving deep into a technique. It's really worth it. But now we have this positive model. The advantage are, as I mentioned, besides finding good distinguishers, we can just extend it for the key recovery. And then we can take into account the techniques in key recovery, like meeting the middle, key bridging, and so on and so forth, right? So we decided to do that, to propose a model that finds a complete attack. But before I explain our model, I have to explain the partial sum technique, which is the most common technique in key recovery of integral attack and zero correlation attack. Then I will tell you how we model this partial sum technique, and we put them together with our model for distinguisher to find a complete package, to find a complete attack. So in integral distinguisher or integral attack, typically we have an intermediate state like X here, which has a zero-sum property. And you want to reach to that point from the ciphertext. This here represents the key recovery. So we start from the ciphertext, we guess the key, and then we check the zero-sum property of X. But the complexity of this approach, if you assume that you have a pool of ciphertext of size n, then the time complexity is n times to the power of k. This is the naive approach, right? The idea of partial sum technique is breaking down the decryption steps into smaller steps and then doing them a step by step. But what's the advantage? As you can see in this shape, the visualization, when you approach from C to X, the intermediate data that you should process becomes smaller and smaller. If you look at this shape, if you start from ciphertext, you do one round decryption, you reach to the you go one round deeper into the decryption. The data that you should store and process for the next step becomes smaller and smaller because of the nature of the propagation of a property in the recovery. If you want to retrieve one cell here, the number of cells that are involved gets larger and larger. But if you want to move backward, the number of cells that you should process gets smaller and smaller. This is the idea of partial sum technique. And let me give you an example. This is a 6-round integral attack on AES. As you can see, if you activate the diagonal of input, then we have a balance property after 4 rounds. Then we attach 2 rounds for the key recovery. Imagine you want to retrieve the first cell of C4 at the top. Then as you can see, the 4 bytes of the key are involved, right? 4 bytes of the key are involved according to this relation. And you have a pool of ciphertext of size to the power of 32 because you have activated the diagonal. And each balanced position gives you 8 bits filter to filter out the wrong keys. You need to repeat this process 6 times at least to uniquely receive the key. So the complexity would be 6 times to the power of 32, the size of ciphertext, times the number of keys that you have to try. The complexity is to the power of 74, more or less. Keep it in mind. I want to surprise you. The complexity of partial sum technique is to the power of 52. Just compare it with to the power of 74. It's incredible. It decreases the complexity significantly. But how it works, as I explained, you start with a ciphertext stat. You guess a few bytes of the key, not all of them. Then you go 1 round deeper and store the intermediate data that you need for the next step, okay? But the point is that, as you can see in this shape, when you go deeper into the decryption, the number of cells that are involved gets smaller and smaller. So the number of data that you should process in each step gets smaller and smaller. The complexity of each step in this process, in this tree, is roughly to the power of 48. So there are 4 steps. You have to repeat it again 6 times. The time complexity is to the power of 52, S-box evaluation. This is the partial sum technique. But how we automate this complicated step-by-step strategy? I just give you the core idea. You can refer to the paper to see more details. This table at the bottom represents each step of partial sum technique. And each step has its own memory and time complexity. But if you look at this table, if you know in which step you should process each cell, everything else is known. If you know in which step you should process each cell, everything is known. It means that we should find the step number in which we process each cell. So for this purpose, we assign an integer variable to each cell, which determines the step number corresponding to that cell. For example, if the label on this cell is 0, it means it is processed in the first step. If the label here is 2, it is processed in the second step. Look at this table. It goes to the second row of the table. If I give you these information, then deriving all of the information on the left is really easy. I'm confused by left and right. Anyways, you need to derive this, right? So you assign an integer. Oh, what happened? My time is over? Okay. If you have this information, then you have everything else. So for that, we assign integer variable. What? Sorry for that. I think some strange things happening. It's okay. Yeah. Yeah. So our model for the key recovery actually determines these labels, right? Now imagine we have a positive model for the distinguisher. We have another CP model for the key recovery, which models the partial sum technique. Just put them together, set the objective function to minimize the time complexity. Then this gives you a model to find a complete integral attack, but not for every cipher, just for a strongly aligned ciphers, right? The black box view of our tool is like this. You need to just give the tool the length of the distinguisher and the number of rounds that you want to attach to the key recovery. And then it gives you a complete attack like this. We discovered this 8-round attack with our tool, but in one step. And it really gives you the complete attack. You don't have to anything manual. You know, it's not like some of the tools for boomerang or differential in which you still have to do some manual tasks to do the early abort technique and all of those techniques in the key recovery. It gives you really the complete attack. But the downside is that it works well for strongly aligned designs, not for weakly aligned designs like present or Symmetric. So this was one example. You know, with the positive model and this relation, we reach to this point that we have a complete tool. But it's thanks to the relation between the zero correlation and integral attack. And these are some key recovery attacks that we discovered with our tool. I think the best improvement was 3 rounds improvements over the previous work. Like, for example, this version of Skinny. The attack that we could find covers 26 rounds, but the previous one covers 23 rounds. This was, I think, one of the best attacks that we could find. Okay, now I want to propose an open question. Actually, as I mentioned, we discovered these attacks based on the relation between zero correlation and integral attack. But the question is that, can we find a positive model for division property or monomial prediction? This is still an open question because the models for division property and monomial prediction are negative models. I have also mentioned some of the downsides and like some of the pros and cons of the different approaches. For example, monomial prediction is really a perfect method. It can capture almost all of the integral properties, but when it comes to practice, it's really slow for a large number of rounds, especially for tweakable block ciphers with a large tweak. This is the downside, but the downside of a method based on ZC distinguisher is that, of course, it cannot capture all of the integral properties. It only, you know, the relation is just kind of one way. If you have a zero correlation distinguisher, it is converted to integral distinguisher, but the converse is not necessarily true. We cannot capture all of the integral properties, okay? I want to, you know, we use the theoretical links between attacks to reach to this point, but sometimes there is not a theoretical link, but there is a structural similarity. Let me show you one of these. Just look at these two shapes. They're really similar, right? This represents a boomerang distinguisher. This represents a differential linear solution. What do you think when you just look at these two shapes? They're almost, I mean, from some aspects, they're almost the same. They're a combination of two differential, like differential linear, two type of distinguishers, right? So in EuroCrypt 2019 and in Crypto 2024, like some kind of links between the boomerang tools and the differential linear tools were discovered that are represented in this slide. As you can see, for each table in boomerang, we have its alternative in differential linear. Actually, this DLCT proposed in this Eurocrypt paper, and the rest were proposed by us in Crypto 24. We just transformed and translated the tools in boomerang analysis into differential linear analysis. Because when actually I started studying differential linear, I just realized that, wow, it's kind of similar. We can just reuse the insight and advancements in boomerang analysis from boomerang analysis in differential linear. And people didn't care about this link, actually, back then. Yeah, sure. Yeah, sure. So I'm going to finish. This is one example that shows how we can use these tables to drive to estimate the correlation. And this shape represents again the automatic method that we can use for both boomerang and differential linear. I just skipped that. This is also a result that we achieved with our approach. But I'm going to finish my presentation with proposing some future works. First, the lessons that we learned. Please consider the theoretical links and structural similarities between attacks when you want to do something. Maybe there is something faster out there, but you're ignoring. But the future works, I believe the connections between attacks have not been well utilized so far, to be honest. We don't have too much knowledge about the relation between attacks. And if we find a relation, maybe we can just reuse the most efficient tools from one attack type to another, okay? This is one point. And I would say a lot of tools that claim a tool for finding complete attack, like our tool for impossible differential, is not really complete, I would say, because there are still some manual works out there you should do. It gives you the initial solution, but you still need to do some manual steps after that. It's not, I think, in exact sense, it's not complete. So this is, there are still some gaps out there. We should fill them. I want to finish this talk with a sentence of my mom, actually, which is relevant to cryptanalysis. You know, in this world, there is a universal law. To gain something, you have to lose something else. If you are actually working on cryptanalysis or automation of cryptanalysis, you cannot achieve efficiency and accuracy at the same time. If you want to achieve accuracy, you need to lose some efficiency, like the tools for division property monoid prediction. And if you want to achieve efficiency, you need to lose accuracy. This is a universal law. You cannot break it. If you go that direction, it's wrong, I think. You should be, I think, careful about that. Thank you so much for listening. Let's go for lunch. But before that, sorry for going over time.